Okay, 7.2, the Pythagorean theorem and its converse. Objective. Students will be able to use the Pythagorean theorem and the converse of the Pythagorean theorem. Okay, this is a theorem we have seen several times before, so this lesson should not be all that new to you. In fact, I don't think it'll be new at all. But here's the basic concept. If you have a right triangle, then if you were to call this side A and this side B, and the hypotenuse C, then you could say that A squared plus B squared equals C squared. And that's really it. And so you can use that formula to find any missing part. If you have any two, you could find the missing one. So let's give that a shot. First one, they tell us that A equals 1, B equals 2, and we don't know C. So just plug it into the formula. 1 squared plus 2 squared equals C squared. Well, 1 squared is 1. 2 squared is 4, so that's 5. So we say C squared equals 5. Take the square root, we get C equals square root 5. Boom. Done. That's it. Try the next one. A equals 5 and B equals 7. I'm going to do this one in blue just to change it up. So we could say that 5 squared plus 7 squared has to equal C squared. Well, 5 squared is 25. 7 squared is 49. So that equals C squared. Well, 25 plus 49 is 74. Yeah, 74. And so if you wanted to take the square root of both sides, I'm trying to save space here, so I'd get C equals square root 74. Now from here we can kind of break this down and get a little bit simpler. I know that at least a 2 goes into that, so 2 and let's say I think 30, let's see, we could do 35 plus 2, 37. Is that right? 2 times 37? Yeah. So that doesn't break down at all. So we would just get C equals rad 74. That's as much as we can break it down. Okay. Next one. I want you guys to try this on your own. You got A equals 6, B equals 2. Find C. Go for it. You may need to pause the video and try it on your own and then come back to it. Here's what I got when I worked it out. I got C equals 2 rad 10. So, there you go. This practice number 2 is a little bit tricky because they give us A and C now, and they want us to find the length of B. So that's not that big a deal, but we just got to make sure we put everything in right. So we would say 4 squared plus B squared, because we don't know what that is, equals, sorry, not C squared. Sorry, I don't know what happened there. Let's try that one more time. 4 squared plus B squared equals, and not C squared, but 10 squared. So we could write that that's 16 plus B squared equals 100. And then we could subtract 16 from both sides. And we would get that B squared equals 84. Square root. So we would have B equals the square root of 84. Now that can break down. In fact, let's see, I know I could pull a 2 out. If I pull a 2 out, I get 42. I can divide that by 6 and 7, and 6 can go 2 and 3. So there's the pair I was looking for, and here's the loners, 3 and 7. So that means that, kind of running out of space, but that means that B equals 2 rad, and 3 times 7 is 21. And there we go. Okay. That should be pretty easy. This also is a concept that we've touched before, but we haven't spent a lot of time on. There's a lot of numbers called Pythagorean triples, and these are 3 whole numbers, whole meaning non-fractional, non-decimal numbers, that make A squared plus B squared equals C squared true. So they just always work. All right. So here's some over here on the side. 3, 4, 5. 3 squared is 9 plus 4 squared is 16. So 9 plus 16 is 25. What do you know? That's the same thing as 5 squared. 5 squared is 12. I'm sorry, 5 squared is 25. And 12 squared is 144. And 144 plus 25 is 169. What do you know? That's what 13 squared is. I don't know what 15 and 17 squared are, and 7 and 24, 25. I don't know those ones off the top of my head, but put them in a calculator, I guarantee they will work. So what I want you guys to do is see if you can come up with a couple other ones. Something interesting, 3, 4, 5 works even if you double everything. So you could say 6, 8, and 10. That works too, so that could be one of yours. And I'll let you see if you could find another one that works. So just give it a try. Try a couple different numbers. But there's a lot that work. Okay, let's move on. This is the important stuff. Kind of the new stuff. This says, Theorem Sum 5, if a squared plus b squared equals c squared, then we know the triangle is a right triangle. So we can actually use that information to tell if it's a right triangle or not. So, we can get these numbers here. It says a triangle has like 16, 48, and 50. Is a triangle a right triangle? Well, okay, first of all, you may look at this, you may think like, well, what's my A, what's my B, what's my C? Well, here's the trick. The biggest number is always your C. So there's your C. And then the A and the B doesn't really matter which is which, but I could just do A as the smallest and B as the second biggest. Okay, so what we're going to do is we're going to say, hey, does A squared plus B squared equal the same thing as C squared over here? Well, let's fill it in. So we got 16 squared plus 48 squared. So we're going to figure out what that equals. And 50 squared. Figure out what that equals. And 16 squared is 256. And 48 squared, I don't know that off the top of my head, so I'm going to put it in the calculator. And I get 2304. Add those together and I get, what is it? 2560. Okay. Well, let's see if that's the same thing as 50 squared. So put 50 squared in your calculator and you get 2500. Well, those two numbers are not the same. So since a squared plus b squared does not equal c squared, we could say, no, not a right triangle. All right. Very good. Let's go on to the next page. All right. On this one, I want you guys to try this one on your own. So just like I did in the last one, I said 10, 24, and 26. And I already know that 26 is my C, and these don't really matter, A or B. It doesn't matter. So trying to see if you can figure out if this is a right triangle. And I'll just let you guys do that. So you may want to pause the video now and try it on your own. All right. Here's what I got when I did it. 100 plus 576, that is 676. So 10 squared is 100, 24 squared is 576, and 26 squared is 676. So yeah, this works. So yes, this is a right triangle. Boom. All right, this last one is where it gets a little tricky. So let's read it. It says PQR has coordinates P32, Q -36, and R 55. Use the distance formula to verify that the triangle is a right triangle. Okay, well, first thing we're going to need to do is we're going to need to plot all these points. So let's plot some points. I'm going to zoom in so it makes it a little bit easier for me. So P is at 3, 2. Well, that's right there. Q is at -3, 6. So that is right there. That's Q. And R is at 5, 5. So that's right there. Okay. Now, if you can see that what we're going to do is we're going to use the distance formula to find the distance of QP, QR, and RP, and we're going to figure out if this is a right triangle, if it satisfies the equation a squared plus b squared equals c squared. What's interesting is we just created a whole bunch of little right triangles. You may not have even seen it, but look, if I go straight over and straight down, there's a right triangle, there's a right triangle, and there's a right triangle. And that is actually what the distance formula is based on. I don't want to spend too much time on that, but the distance formula and the Pythagorean theorem are really the same thing and just kind of reworked. So I'm going to zoom out and we're going to try and find the distance of all these guys. So let's do QR to start off with. Well, you can plug it in the distance formula if you want. I'm not going to do that because I think it takes too long. Instead, I'm going to just use the Pythagorean theorem, and I'm going to say Q to R is 8 to the left and right, so that's what I would get if I did x2 minus x1. I would just get 8, and so I'm going to square it. And it is only 1 down, right? So we go 8 over and 1 down, so I can say plus 1 squared. Well, I know that 8 squared is 64, and 1 squared is 1, so 64 plus 1 is 65. And it looks like that would be my hypotenuse, right? If anything is a right angle, it's probably this guy right here, so QR is going to be my hypotenuse. So that's going to be my C. Okay? Let's try QP next. Well, I'm going to do the same thing that I did before, and I'm going to go 1, 2, 3, 4, sorry, counted too fast. 1, 2, 3, 4 down, and 6 over. 4 down, 6 over. So I would have gotten a 6 squared here for my x2 minus my x1, and I would have gotten a 4 squared here for my y2 minus my y1. 6 squared is 36, and 4 squared is 16. Together that makes 52. And I'll go ahead and call this my B. And lastly, I'm going to do PR. Okay, PR, look at that. 2 over, 3 out, easy. So I'm going to say 2 squared plus 3 squared. And 2 squared is 4, 3 squared is 9, so that is going to be rad. 13, we're going to call that my A. So now, they want us to verify whether or not this triangle is a right triangle. So let's plug it into the formula. A squared plus B squared should equal C squared, and let's see if that's the case. Well, my A is rad 13, and I'm going to square it. My B is rad 52, and I'm going to square it. And my C is rad 65. I'm going to square it. Well, you may have already seen this, but don't my square roots and my square just cancel out? Of course they do. So I'm just going to cancel these guys out. And so I'm left with the equation 13 plus 52 equals 65. And sure enough it does, right? 13 plus 52 is 65. So yes, we verified that this is in fact a right triangle. That means that that is a right angle. It also means that these lines here, PR and QP, are perpendicular. So it's kind of neat just from that one problem. So summary is, explain why a Pythagorean triple can represent the measure of the sides of a right triangle. So go back to the Pythagorean triple and see if you can explain why that will always work. Okay. Adios.